Very good. Today we have Marco Meineri talking about this recent paper, Bounds on Photon Scattering. And please, we thank you for accepting our invitation, and please take it away.
Thank you very much for the invitation. Yes, so I will tell you about bounds on photon scattering. So this is a paper that came out recently with this set of collaborators. And okay, let me get straight to the outline. Let's not waste time. So I will start by motivating a bit. Why would you want to go into this sort of technical tour de force, except well, aside from masochism, which is of course a big pulling factor towards projects in our lives. And so this is going to be the first part. I'm going to give some notion of how does light by light scattering look like in at low energy. So this is going to be an effective field theory part, and this is going to, for us, establish what is the input we want in order to single out our S matrix among the infinite possible S matrices. Okay, once we understand the low energy effective field theory, we'll have to sort of set up the numerical problem. This is going to be done in part 3. And then we'll finally get STPB, so the computer, to work hard for us and give us some plots, which we're going to examine there. Part of the features of these plots are going to be explained by weakly coupled things that we understand to a good extent. This is going to be the subject of part 5 of the talk, and then I conclude. At any moment, please stop me for questions, but only easy ones. Okay, so why is this now? Then I will have to do this every time, which is fine. Okay, so motivation. So, well, okay, this is going to be kind of quick, but let me still go through it because it's nice to motivate things even to an audience which knows them better than you. So, okay, so there was at some point a couple of papers that restarted, refueled the idea that we could study non-perturbative S matrices just by constraining them through crossing, analyticity, and unitarity. So this revival has produced a lot of literature, and it's essentially driven by a central idea. The central idea is that the space of unitary, very important, crossing symmetric amplitudes is convex. Okay, so this is why we can easily apply things. When things stop working, it's not nice. Okay, yeah, I just want to do this. Why we can easily apply this like well-known numerical methods to this problem. So I'm going to review briefly why that's the case. So why it's important? Well, for bootstrappers, it's obvious by now. The idea is that convex problems are easier to solve, at least numerically. Convex optimization methods in particular are particularly efficient in finding boundaries of a space. The idea being that there's never a local minimum, right? If you have a convex space, you'll run into one direction, at some point you'll hit the wall, and either this wall is exactly perpendicular to you, then you're done, or if it's at an angle, then you follow the direction and you will eventually get to the minimum. So there's no reason to get stuck into local minima, so the optimization is efficient. And in practice, this optimization will be for us performed by this nice black box, which is STPB, which was developed for a conformal bootstrap application, but in fact it just solves a mathematical problem in convex sums of matrices, which works equally well for S matrices. So what is this? This is part of a general bootstrap program, which, okay, the usual propaganda is that it aims at picking just symmetries of your theory, imposing unitarity, and imposing some low energy input in order to single out what is the theory you want to study. And this spits out constraints on observables. Okay, so it's it's kind of obvious why you want to apply this philosophy if it works to as many things you can. So it started with conformal field theories. This was the big breakthrough. Okay, this is the seminal paper by these people. And then it continued to, was extended to S matrices, which is what we're talking about today, to many other things, quantum field theory in ADS, to quantum mechanics. It has possibly many applications in many different topics, expectation values of Wilson lines in gauge theories. I mean, there's many things and probably many more to come. So, okay, so let's, this is essentially why we would like to, or well, better yet, how we would like to solve the problem. The why, well, it'll come in a moment for a specific case of a photon, but sort of obvious. In any case, let me take a detour here and explain better why unitarity is giving us this gift of convexity in the specific context of S matrices. So an S matrix is just an overlap of state, well, an out state and an in state. This is a matrix element. And okay, this being an overlap as a constraint because it's a piece, it's an element of a positive definite scalar product if we are in a unitary theory. So in particular, in this subspace, unitarity reduces to that. And so, okay, so we just write down what the scalar product is, and we get normalization for the state on the diagonal part and the S matrix in this off-diagonal part, right? So the fact that this is positive semi-definite is a manifestation of unitarity, or, well, I should say, well, okay, I guess it's a matter of names. So having a positive definite scalar products implies something which we call unitarity, means in this case that SS dagger is less than 1. Okay, so this is good. It's the usual condition. Why is this a convex condition? Well, this is just a statement that if we take linear combinations of S matrices, say some S1 and S2, in which both terms obey this condition, the linear combination here is just alpha times 1 S1 S1 1 plus 1 minus alpha of the same with S2. And it's still positive semi-definite because it's a sum of positive semi-definite terms, as long as the combination, the parameter is bounded like this, which means that this is a convex combination, right? So this is convexity. This just means that because of unitarity, the space of cross-symmetric unitary S matrices is convex. And so, okay, so we are in business. We can just plug all of this into STPB and get bounds. There is, in fact, a bit more of work, some technical work. And essentially, this technical work is, okay, we need to understand what do we mean by in and out, because this in and out have some indices, or more concretely, they have some properties under transformations for around under Lorentz transformations and any symmetries which commute with the S matrix. And we should be mindful of those symmetries and choose the right basis. In particular, okay, since the theories we want to look at are Lorentz invariant theories, we should go to partial ways, which is just the basis of eigenstates of the Casimir of this of the Poincaré group. So this is a bit what's coming. So what we'll have to do is essentially pick this basis to some extent and pick some features of the S matrices once the basis is picked, or perhaps the reverse in the order which I'm presenting things here. Okay, are there questions up to this point? If there are no questions, I'll proceed. So there's been two big avenues in looking at this problem, which is essentially studying non-perturbative S matrices in, say, modern era, and in particular bounding low energy coefficients, which is what we'll do today. There are numerical methods, which is what we'll talk about today. So I will not spend time now on this, except giving some specific instances where this was used before. And there's analytic methods, which I'm only going to touch briefly on towards the end of the talk. But okay, I reported here a couple of references about this. And I just want to say, why would you like to use numerical methods if you have analytic methods, right? We would always like to use analytic methods, but in general, these analytic methods need a small parameter, while what we would like to do doesn't have that. This is not necessarily a bug, as long as you could take this parameter to be small, but parametrically small, meaning that you can take into account corrections, which is actually not completely understood in this context. I'll come back to this maybe if time permits. So it's a feature, and it's possible that a hybrid of these two methods are going to be more useful in bounding things which are closer to the real world. This will be particularly true in the case of photons, as we'll see later. There has been work on photons specifically using these analytic methods, and I'm putting the reference here. So we'll compare to this at the end. As for numerical methods, what have people done so far? This should not be here because it was copied below. Well, they've been asking many questions, and they've been putting out very nice papers, of which this is not a complete list. Essentially, well, okay, you can ask about couplings. You can ask what is the cubic coupling or the party coupling appropriately defined for a theory in which you have massive scalar particles. Maybe one or maybe multiple of these particles with a low symmetry, or with some global symmetry so that they're degenerate. You can also, closer to what we'll do today, put bounds on effective field theory coefficients, what's called Wilson coefficients. In this case, since it's low energy coefficients, you want the low energy theory not to be empty, otherwise it's completely trivial what you're going to do. So a theory which has a massless scalar. So massless scalars arise in a variety of contexts, essentially every time there's something that protects them. For instance, Goldstone theorem. So in particular, you can do this in the chiral limit for QCD, and in that case you get massless pions, or you can do this in another context in which there's been exploration. This first paper has been about the excitations over a flux tube over a long string, which are protected by breaking up translations. And then you can do something which is slightly more exotic, which is looking at scalar superpartners of the graviton, so that you are putting bounds on allowed theory of gravity in higher dimension, or at least supergravity in higher dimension, and you can compare with the values that come from string theory. So all of this has been done, and the only thing I want to emphasize is that this is so far has been essentially restricted to scalar particles. This is for technical reason mainly. So at some point somebody had to try to break through and put spin in the game, and this is one of the motivation of what I'm talking about today. So what is the next step? Which is a natural step. How about particles with spin? This the kinematics for this was sort of elucidated in a recent paper by my collaborators that did a lot of archaeology and some improvement. And today what we do is to apply all of this to the case of massless spin-1 particles in 4 dimensions. Okay, why do we do this? well, except for the challenge of like going up in spin, this is sort of a very natural scenario for low energy effective field theory, because our word at low energy is indeed a word of photons. More precisely, is a word of photons and gravitons. So even more interesting would be the spin 2 case, which is sort of the next step in the ladder. So maybe you'll have a seminar in the future on that. And then it's also nice that there were analytic results, so with which we can compare. And these analytic results have an assumption of perturbation theory, the small parameter I was saying before, while we'll have fewer assumptions and will give non-perturbative results. The price we'll pay, as we'll see, is that we'll bound a very large space, and not necessarily our word leaves any closer to an edge if we don't make any extra assumptions. So there's room for improvement on that side. Okay, so question about this? Great. If there are no questions, we can move on to something more concrete. And in particular to the effective field theory of photons, what we want to study today. Okay, so what are photons? Photons are massless spin-1 particles whose scattering amplitudes are soft in the IR. So, okay, massless spin-1 particles is kind of obvious. That's how they're defined. And the fact that they're soft in the IR is sort of a consequence of the fact that they are massless spin-1 particles and live in a Lorentz invariant theory. And this is sort of an intricate set of steps that I'm not, I don't know how to simplify these steps very directly, but essentially, if you want to describe, I guess the most historically compelling argument is that if you want to describe these particles, you have to use a field which is a vector, and then the mismatch of degrees of freedom will force a new gauge invariance, and then this will put constraints on the low energy effective field theory. All of this is sort of tied together and made very obvious by a Lagrangian. So since we're going to low energy and to an effective field theory, we're very welcome to use Lagrangians because they will predict the complete non-perturbative physics up to a certain order in the momentum. That's what usually happens in effective field theory. If you go to low energy, you have a tower of irrelevant terms that don't matter. And so the first few terms in your Lagrangian will give the full result. And this also put together all these physics that gives specificities of photons interactions and makes your life easier. So we're just going to use it, and we're going to use that. So we should write a theory, which is a theory of a spin 2, well, sorry, not a spin 2, of a antisymmetric field strength. And essentially the whole story comes out because this field strength has a derivative. So since we need to use this, there's going to be some power of the momentum in any vertex, which will make the amplitude soft at low energy. Okay, so what do we write here? Well, there's some free propagation term, and then we start with our effective field theory. We will write what we can. So at so we're interested only in terms with 4 field strength because we want to study 2-to-2 scattering. And then we need to organize the expansion in terms of derivatives. So at 0th derivative, or say minimal number of derivatives, which is dimension 8 operator, we have this contraction, and we also have another contraction with another coefficient. And then there will be many other terms with higher derivatives. And this is assuming parity. I haven't put any epsilon in, so this is an assumption we're going to make to simplify a bit the kinematics. It's just a technical assumption. One could relax it and do the same. Okay, so this is sort of a very simple step, and it creates what's known as the Euler-Heisenberg Lagrangian. and it tells us that there are only two coefficients, the C1 and C2, which contribute at leading order in a low energy expansion. So what does this Lagrangian buy to us? Again, it buys us a derivative expansion. So the fact that there are finitely many terms in this Lagrangian that contribute to any order in the momenta, where P are external momenta. And N is finite, right? Any finite order, you only have finitely many terms here. Again, the reason is that there's derivatives here. And then it gives us our targets. So these guys are Wilson coefficients, are targets for natural targets for the bootstrap. They tell us something about what the low energy scattering of photon looks like. Essentially, they fix it completely at low energy. Right. So the question is, yeah.
It's just that probably it's too early to ask this question, but since you said before that you didn't find our world in the corner of your space of in C1 and C2, does is Born-Feld special?
Sorry, I didn't get the last piece of the sentence of the question. So somebody can repeat.
The Born-Feld action is special for you. Will it be like the C1 and C2 of the Born-Feld? Is it at some corner or is it also there in the middle?
Oh, yeah, that's a good question. It's something that at some point we wanted to look at and then sort of we forgot about Born-Feld. I'm not sure. I mean, it will be, sorry, let me think for a second. As long as you can expand. So there is a question of what you mean, right? In Born-Feld,
right? Born-Feld is an expansion of this type.
Yeah. There's an expression for C1 and C2, but it depends on an extra coefficient. Right, so there is in the Born-Feld, there is something like there is a combination of the metric and the field strength, and there is one coefficient in between, and then the question is how big is this coefficient? When this coefficient is small, it will have the same features as all the rest, so it will leave not in the it will leave at some, in a sense they all leave at close to some boundary, but it's sort of the uninteresting boundary because it's a weakly coupled boundary, is the one in which we don't need or we don't use much of the power of STPB. Then the question, if you pick this coefficient big, what's going to happen? And I am not sure it's possible. Yeah, so okay, we'll find some bounds on some of these coefficients. I'll have to say the bounds on C1 and C2 are actually you can find analytically. So I suspect that for the all, since you can find analytically for the all range, and since Born-Feld is fixed by one coefficient, for the all range of this coefficient, the amplitude will just be inside those bounds. Although I'm not sure of what is the regular limit of Born-Feld, but if it's less than 2, then it's fine. If not, I mean, and then we'll find some non-trivial bounds on something that is in the dot, but it's sort of too complicated to write in the Blackboard, so we'll see it in the amplitude. And those will also depend on the coefficient in Born-Feld. I'm not sure if that imposes stronger bounds on the strongly coupled side. This is something that we should have looked at, but we didn't. So maybe in D2, I can tell you. But in the limit in which Born-Feld should describe close to our word, so in which this coefficient is small, then it sort of doesn't give us any, I mean, STPB doesn't give us anything new. I'm not sure in the other corner. Also, because there is another problem, yeah, it might also be that it's not possible. I mean, this Born-Feld expansion will have some radius of convergence. If this coefficient becomes big, I guess then you just cannot expand.
Yeah.
And then it might not be easy to get the answer. Although low energy, you should always be able to expand. Yeah, okay. Maybe we can discuss this later. It's an interesting point. I think we should have just gone for it, but it was a bit. We ran out of steam. Okay, so we'll ask what are the bounds on these coefficients. And in order to do that, we need some low energy input, as I was saying. So let me be a bit more precise on how this Lagrangian gives us our low energy input. Well, of course, it gives us fully, but it's sort of interesting to see without doing many computation, how much mileage you can get from these Lagrangians. It also gives some physical intuition on why things are the way they are. So what are the consequences of this low energy effective field theory for the 2 to 2 amplitude T, where as usual we are splitting the S matrix in 1 plus I curly, oh come on, curly T. I don't know why curly, but this is the way it came out. Okay, so the first consequence is sort of a more specific incarnation of the softness I was saying. So if we are just a little bit more specific, we can see that the first vertex that we can write goes like energy to the 4th. So this means the T goes like energy to the 4th plus energy to the 6th. Okay, so it's soft at low energy, it goes to 0, and it goes to 0 with a specific power. Then we can discuss inelasticities. When do inelasticities start? Well, of course, they start at any energy because we can produce photons with energy, but at which power in at small energy in the effective field theory? Well, in elasticity, we'll start with an amplitude of 2 to 4. And so this term is a term I didn't write there, but it's f mu nu to the 6 with whatever contraction, it doesn't matter. It still has 6 derivatives, so it will be energy to the 6. So this has an immediate consequence, which is that the S matrix is actually fully unitary, it's just 1 as a dagger, up to orders, sorry, energy to the 12, the square of that, because we need to, well, we have SS dagger. Okay, so it means that up to energy to the 10, we can use elastic unitarity. Elastic unitarity, what does it mean? Well, okay, in some context, you can write it more or less like this. It means that the imaginary part is fixed by the square of the amplitude. Essentially, well, this will have indices, but if you look at partial waves, you have partial waves in a circle. Sorry, partial waves lives here. This condition, if you look at this condition and you take a scalar case, you'll have that this is a phase. And if you're looking at a generic amplitude, this would be less or equal, so it is a disk. But if it's really equal, the amplitude lives on the boundary of the disk, so there's clearly a relation between imaginary and real part, which is this relation. So this is all what the optical theorem tells you. For us, what does that mean? It means that the imaginary part of our amplitude to order 2n, say energy to 2n, is some function of the amplitude at order n, right? Because I need to take a square. And in particular, since the amplitude we just said starts at order energy to the 4th, this immediately means that the imaginary part of our amplitude starts at order energy to the 8th. So we're understanding a lot of the structure without doing many computations. We understand that we have some amplitude, 2 to 2 amplitude that starts with energy to the 4, and it's real up to order energy to the 8. At energy to the 8, it has an imaginary part, but this imaginary part is fixed in terms of the lower order terms, which are 3-level terms. And then the unknown stuff will start at higher order energy to the 12th. So in order, this essentially fixes completely the amplitude up to the order energy to the 10. And why is that? Because, well, we know only the imaginary part, but we also know that it comes from a one loop computation, essentially because each vertex is the same argument as above. Each vertex is energy to the 4th. So you need to, you can at most put 2 vertices in order to get energy to the 8th, which is the statement that the imaginary part comes from one loop. And so you get that the imaginary part comes from logs, right? There's no more complicated function that come out. Because I'm using a little bit of diagrammatics, but not much. I'm just saying that one loop computation gives simple logs. So what does this allow? It allows to just write the imaginary part using this relation, which relates it to the 3-level, and then write any general expression with logs such that it matches the imaginary part that we computed. This fixes the amplitude completely, it fixes the real part as well. So we conclude that the amplitude is fixed up to this order as a function of the CIs, the Wilson coefficient at 3-level, and mu. some scale that we'll have to fix. Okay, so this is sort of a nice computation that you can do for free. And in fact, you don't ever have to compute a diagram if you don't want to. You just you will just do exactly what I said in Word, and you'll find the whole amplitude, which is what we'll write in a little bit in the talk, like in 5 minutes. Okay, if there are no questions, I can move on to kinematics and setup. But if there are questions, please stop me. Okay, so well, we can go to I mean, we understand now, at least in words, what are the low energy features of the amplitude we want to study, and we are ready to put them in the numerical setup. So we'll have to build it. So how does it work? Well, we'll have to impose crossing and the low energy behavior I explained before into some parameterization of the amplitude. These are the 3 points that I'm going to discuss now. And the parameterization of the amplitudes will have to be linear. Why does it have to be linear? Because of convexity, right? We wanted to use the power of the fact that there is a convex structure. Convex structure means linear combination of the amplitudes, given amplitude still. If we don't pick a linear parameterization, we just lose all of that. Right? So we'll need to have a linearity there. And then we'll impose unitarity. Impose unitarity as a quadratic constraint. So we'll do that numerically. This is where STPP comes in. Okay, so let's start from crossing. What is crossing symmetry for this amplitude? Well, first of all, it's time to be a bit more specific now. The amplitude depends on actual indices, lambda 1, lambda 2, lambda 3, and lambda 4. Each of the lambdas take value plus or minus 1. These are the helicities of the photons. This comes from the fact that photons are a representation of spin 1 of the U1, sorry, of charge 1 of the U1 inside the ISO 2 little group. So this is a very nice story that you can read in Weinberg or in some appendix of our paper. And but you should read it in some appendix of our paper, because in Weinberg there is some annoying sign mistake for one of the generators of the Lorentz group, I think. In any case, this means that there are 16 amplitudes a priori, so this is a lot, that depend on, because of Lorentz invariant, on 3 Mandelstam invariants, which is the usual story. In fact, 2, because of the constraint s plus t plus u equals 0. So, okay, so this is what the amplitude is, and I promised you to talk about crossing, so let's talk about crossing. First of all, of these 16, which could be too big to handle in a computer, or at least, well, for us, Bose symmetry, the fact that bosons are photons are identical particles, and the parity reduces to 5 amplitudes. And okay, you can pick. It's a certain ambiguity, but okay, we decided to pick these amplitudes as the independent ones. This is before crossing. This is just using Bose symmetry and parity. So plus plus to plus plus. So these are the helicities of the incoming particle and of the outgoing particle. So plus helicities do the same, or plus helicities and then you flip the helicities, or etc. etc. And then there's crossing. Crossing will still do something for you. It will mix those things. And so in fact, it creates some relations between them. Remember, for comparison, if you had the scalar amplitude, Lorentz invariance would just tell you that it's some function of 3 variables, if you want to take them independent, and then there's a s plus t plus u projection, equals 0 projection. And then crossing will tell you that in fact, it is invariant on the permutation of these 3 variables. Here, since there are multiple external particles, crossing doesn't tell you just that. It tells you, in fact, that there are some relations between some amplitudes and some others. In particular, if you just work this out with a little bit of patience, you find that there are 3 amplitudes which are independent. And furthermore, they have some symmetries in their coefficients. In particular, we picked as independent bases phi 1, phi 2, and phi 5. Phi 1, phi 2, and phi 5. And phi 2 and phi 5 are completely symmetric in STU. So they're like the usual scalar amplitudes as for crossing, not for unitarity, but for crossing. Phi1 is symmetric in T and U. And then the other amplitudes, Phi3 and Phi4 that we've eliminated, are related to Phi1 by swapping with the argument S. Okay, so at the end of this discussion, we have three amplitudes that we need to parameterize according to the low energy behavior that we discussed before. And then we'll impose unitarity on them, in particular, going to partial waves. So it's now time to come back to the low energy behavior. And well, essentially, after you solve the exercise that I was proposing before, using elastic unitarity up to order S to the 10, you'll get these amplitudes, the following amplitudes. In particular, the following low energy behavior for these amplitudes. Well, let's just coarse grain a bit and say what's interesting about that. First of all, it's they depend on some coefficients, and these coefficients are, I'm calling G, F, and H, are linear combination. In particular, G2 and F2 are some linear combinations of the C1 and C2 I had before in the Lagrangian. You couldn't hope that there's exactly that, so it's some linear combination. And then these other coefficients are all Wilson coefficients in the Lagrangians at higher order. And you see it appears G2 squared, so it's a 3-level, if you want, amplitude that gives you that, but this is the complete non-perturbative behavior at this order in energy. This is the beauty of effective field theory. So there's some terms which are just polynomial because we said the amplitude was real up to order S to the 4th, and then there's L1 and L2, which are written below here. And the only thing that matters here, well, almost the only thing, is that there's logs here. These are the logs that I promised. And the other thing that matters is that these coefficients beta in these amplitudes, in these logs, are, as written below here, fixed in terms of the 3-level coefficients. And more specifically, since I was telling you that the term at energy to the 8th was fixed by the 3-level term at energy to the 4th, 3-level term at energy to the 4th is just G2 and F2, and indeed there's only F2 squared and G2 squared that appear here. So it all makes sense, and then the only computation you need to do is to fix these numbers, which are fixed by the fact that the amplitude needs to live on the circle, elastic unitarity. Okay, so this gives us a lot. It gives us a specific low energy behavior and some logs to which we can match an ansatz, which instead need to extend to all energies. Okay. So what is this ansatz? Okay, I will just very briefly say that we are assuming maximum analyticity. So we are assuming that the only cuts that appear in the amplitude, essentially the only singularities in the amplitude are the ones which are absolutely necessary, essentially the multi-particle cut that starts at S equals 0, T equals 0, and U equals 0, and extend to infinity. And this makes it useful to map these cuts to the unit circle using a simple analytic map. In particular, this maps the upper part of the cut into the upper part of the circle, and the lower part of the cut into the lower part of the circle, and the region around inside the circle. Why is it good? Because then it's very simple to impose analyticity in the rest of the complex plane just by writing a power series in this variable rho, which should converge up to rho equal 1, and will clearly contain no singularities for modulus of rho less than 1. Okay, so essentially this fixes the ansatz, and the ansatz is some generic power series in rho with integer powers that we would like to take infinitely many, but we're going to have to truncate to n max. There's some constraint on these coefficients, which are these parentheses, but and they are just fixed by crossing. So these three coefficients, their symmetries reflect crossing as I explained it before. So in particular, for instance, this amplitude was TU symmetric, and so are these coefficients, very simple. And then there are the logs which are added by hand in order to match the low energy coefficient. I'll come back to them in a second. And some extra variable, which is down here, which is also necessary to match instead the polynomial part of the low energy amplitude. So apart from the details, this yes.
Can you remind us why there are no logs in the third term?
Logs in this term, yeah. So there will be, but at a higher order. So that's a very good question. Here, what are the logs we're inserting here? These are the one loop logs up to which are what fixes the amplitude completely up to order s to the fifth. And up to order s to the fifth, there's just no logs in phi-5. This is something that follows from essentially the well, I mean, it comes out doing the exercise that I was explaining before. So you could generically have logs that order energy to the eighth, but in order to have logs in phi-5 was at a specific kinematics was a plus to plus minus. And you can see that the necessity of flipping one helicity here forces on you a specific low energy factor, which is here is its avatar is this one, but it's in fact is just that low energy is reduces to s times t times u, and this STU already fills you up to order energy to the 6. So here logs will start at order energy to the 12, and now you could put them. And then for consistency, you would have to keep computing here, but then the coefficients will not be fixed anymore because at energy to the 12, you also have particle production. So what is the philosophy here? The philosophy here is to put the logs which are necessary to make well-defined the low energy coefficient up to the order we want to look at them. And we look at them up to precisely the order of the first logs here. And then hope that for large enough n max, the extra non-analyticities on this circle will be reproduced by the rest of the series. Okay, so this is a trade-off. In principle, you could keep going, but you cannot keep going indefinitely. Otherwise, you're not doing bootstrap anymore. You're doing some whatever perturbative computation. You have to put more and more into it. The idea of the primal S matrix is to hope that this Fourier transform on the circle is approximating arbitrarily well any term that you might want to add. So, okay, in this respect, it would be very nice to redo this story using a dual method in order to see that, in fact, this is possible. But for the moment, this is what we have. Okay. So, okay, so then, well, let me just go ahead and discuss unitarity. I will just really say essentially nothing because I want to get to the plots. As I was saying at the beginning, we need to change basis. Why do we need to change basis? Because the S matrix is block diagonal because it commutes with some charges. So we should go to the representations of this group in order to find the non-trivial blocks. This is called the partial wave decomposition. Partial wave decomposition is just a specific choice for the in states and for the out states, which puts them in irreducible representations of Poincare. Irreducible representations are labeled by two Casimirs, p squared, the momentum square, and the Pauli-Lubansky operator, which okay are just the energy squared in the center of mass and the spin. So there's some integral transform, which is just the projection to that basis. So you have the generic amplitude in the generic basis, and then you need to sort of project that. So you take any of these in state and out state, and you project it into one of these states with fixed eigenvalues for these Casimirs, and you get one partial wave. The partial wave depends on S and on L, and it knows about the original helicities. in a specific way, which is encoded by group theory. Essentially, this for a single amplitude would have been a Legendre polynomial, and instead for this spinning particles is something called smaller Wigner-D matrix, which is just a more complicated polynomial that depends on the difference in helicities of the particles. What's important here is that this is all fixed by group theory. So once you have the ansatz here, you need to do some integrals over the ansatz, right? So there will be here, there will be powers of these raw variables. You need to integrate them, you do this numerically, and you get the partial waves. Since the ansatz was linear, the operation that you do to go to partial wave is still linear. So these guys are still linear in the coefficients, this alpha that parameterize your ansatz. Okay, so I will not spend time here to tell you specifically what is the result of that. Let me just say that then you get really for real the condition that we wrote at the beginning, positivity of the scalar product, but now in terms of these partial waves. So depending on the spin, you'll have a different set of matrices. This phi1, phi2 are the original amplitudes. L means that there's a partial wave of spin L. And then this has the structure that is here, 1, 1 as stagger S. There's some of these conditions which are 2 by 2. This is when for a specific spin L, there is only one subspace. There is a dimension 1 subspace that block in the S matrix is non-degenerate. And there are some spins, in particular the even ones, for which there are 4 by 4 matrices, because this matrix, this S matrix, is in fact a 2 by 2 one. So this is the problem you have to solve. You have to impose positive semi-definiteness of an infinite set, one for each L, of some 2 by 2 matrices and some 4 by 4 matrices, with some special cases that are not too important now. And on top of that, you might want, which is what we do, add some extra condition. One condition is separately taking the limit L to infinity and impose that. This is because we're going to truncate in spin. We won't be able to impose infinitely many spin conditions. Doing the same for energy, and have some extra equation which sort of takes into account all the partial waves at the same time, say, for instance, positivity of the imaginary part of the amplitude. This is all technical, not very important. The things to take away here is that there's going to be a cutoff L max, which is the amount of these constraints that we impose. There's going to be, so there was another cutoff, so let me maybe, I don't know if I wrote them below. Oh, yeah. There's going to be a cutoff L max. We impose a unitarity up to some spin L max. There was an N max, which was the maximal power in that sum of terms in the ansatz, which instead is sort of, it tells you how rich is your ansatz. Raising N max gives more freedom to the ansatz. Raising L max gives less because it imposes more constraint. So these two are fighting each other. And then there is a third cutoff, which is less important, which is at which point in S are you going to impose unitarity. And okay, you can choose a grid, which is fine enough, and it's going to be fine. You just check that nothing is changing, that you're not violating unitarity to match in between the points, and that's fine. So this is the end of the technical work. Now we can just define what are the observables we want to bound once and for all, and then see some plots. So the amplitude, I wrote it before, here it is again. And the coefficients were this G. The only thing more to say is that these are dimension full, right? The amplitude has some fixed dimension. In particular, in 4 dimensions, it is massless. All of these are dimension 0. So since there's a rising powers of the Mandelstam, these guys have all their mass dimensions, which corresponds, of course, in effective field theory to higher dimensional operators. So that's all fine. So what are the observables that make sense? These are the dimensionless observables. So in particular, for the dimension 8 operators, these were linear combination of C1 and C2. We need to define some normalization. So in particular, we'll just divide by powers of G2, right? We can pick one of these coefficients, anyone in fact, but it's very natural to choose the first, to set the units. So we'll just measure energies in units of G2, whatever G2 is. So this means that you shift the S by square root of G2, and then this means that all these guys become dimensionless combinations of G3 divided by some power of G2. That's trivial. In particular, dimension 8, G bar 2, which is the dimensionless relative of G2, is just G2 divided by itself. So it's just 1. This is what fixes units. And then we have F bar 2, which is this ratio. Okay. And then we have coefficient of dimension 10 and 12, and these are all what we're going to look at, which goes up to where these logs kick in, included. And then you see that there's different powers of G in the denominator. Here, for instance, it's 3/2. This would be 5/2, etc. Okay, so the barred coefficients are dimensionless observables, dimensionless non-perturbative observables. They're our goals, our target. So we'll just fix some Wilson coefficient and ask for the maximum and minimum of some others. This is the game we can play. Okay, is it all clear? If so, we can go to plots. Okay, so now the rest of the talk. Do I have 10 minutes?
Yeah, you have more if you want. But...
No, 10 minutes should be enough. But okay, great. So the rest of this is going to be divided in two parts. One is we go through this dimension 8, dimension 10, and dimension 12. We see what we find. And then we'll find some features which are, say, perhaps less than what we would have hoped for. And then we try to explain it and we find that it was, in fact, in some cases, simple, why this had to be the case. And that would be our last point in the talk. Okay, so we start with dimension 8 coefficients. These are the leading ones. And we find that to a very, well, convergence is very fast here. So it's pretty clear that the bounds are less or equal than 1 and bigger or equal than -1 for the only coefficient that is dimensionless, which is the ratio of the two, F2 divided by G2. And in fact, this result we knew already, it's exact. It comes, if you want, as a variation of some whatever the story that started with this paper, to some extent at least, about infrared obstruction to UV completions. And in modern terms, it just says that the coefficients G2 and F2 are dispersive. It means that they can be written as integrals of a kernel times something positive. Well, the kernel is positive, and the other thing is something that depends on the amplitude. So in particular, the combination G2 plus F2 and G2 minus F2 are the integral of some imaginary part of some combination of the amplitudes that we had, phi1, phi2, and phi3, with different sign depending on this sign, with some kernel. And okay, this is not completely trivial, but you can check that this combination has a positive imaginary part. Yes, okay, so then since it has a positive imaginary part, these both are positive, so you get these two lines and the couplings needs to stay here. So if you write F2 divided by G2, you're just moving in this direction and you get from this, or maybe even better, moving in this angle. And then you go from slope 1 to slope -1, this is this bound. Okay, so we are good. I don't know if I want to explain why this combination is positive, but maybe you can ask me. If it was a single amplitude, then it would just be the usual optical theorem. For multiple amplitudes, essentially the only complication is that you need really forward amplitude to use these things, right? So you need to make sure that the out and the in state are the same. And since we had combination, these phi's were a combination of different helicities, you need to take linear combination of in states and out states that are the same combination. This gives you positivity for some specific linear combination of the amplitudes, which is why here not all couplings are directly related to a positive imaginary part. Okay, so there's another piece of the story, which is that these bounds are realized they realized as some weakly coupled limit of what we call partially recompletion. So the idea is we had our scattering of photons with some vertex here, and we blow up the vertex by saying, well, let's insert a resonance. And if you put scalar resonance or pseudoscalar resonance, so some massive particles, and you take the limit in which they are very weakly coupled, you'll get the amplitude to saturate these bounds. There will be, this essentially will be the game we'll play in the last part to explain some features of the plot we find. Okay, so let's go to dimension 10. And at dimension 10, you find the interesting result that there are no bounds. So you just go with STPB in all directions, and STPB will always find that there exist amplitudes with some larger value of these Wilson coefficients in absolute value. And there is, in fact, an analytic explanation of this. And here is the first departure from, say, these analytic methods, which are essentially what I showed for the dimension 8 coefficients on steroids. Since in the analytic methods, if you assume some weakly coupled limit up to some scale, you have extra scales in the game, and you can define different observables. Those different observables might be bounded in, say, 3-level approximation. But once you remove that scale, once you say, well, the amplitude has to be generic, the statement is that as the scale in which you're allowing for dragons to appear goes to 0, you're allowing dragons all the way to energy 0, then those bounds go away. So in the completely non-perturbative case, there are no bounds for dimension 10 coefficients, at least if you just consider 2 to 2 amplitudes. Okay, and so essentially this is also the reason why we went this far in the low energy theory. We had to do a sort of a more thorough job because at dimension 8 everything is fixed analytically. At dimension 10 there are no bounds. At dimension 12 instead there are some strongly coupled. There is some strongly coupled physics which one could study through STPB. So, for instance. So at dimension 12, the couplings were the ones that had the label 4. So for instance, G bar 4, there were, for reference, G bar 4, G bar 4 prime, F bar 4. These were the 3 couplings at dimension 12. And for instance, if you look at G bar 4, you'll find that there is no maximum. Again, it's one-sided bound, and there is a minimum. And this region, so from next part, then we'll see that everything that leads up there is weakly coupled. Well, not necessarily everything, but sort of morally everything is weakly coupled. Stuff we know.
What was F2 bar? Sorry, is the coupling of
yes, yeah. So G4. You mean the bar?
F2 bar, the horizontal axis.
Okay, very good. Yeah. I was going to remind you that of that. Yeah, thank you. So F2 bar was F2 divided by G2. So the point is what? The point is the following: that you could just ask for what is the minimum of G bar 4 overall, for instance, right? What is the minimum of this coefficient? But it's sort of better to ask for fixed value of F2 bar. And why is that? Because G bar 4 was, if I go back to the amplitude, was coming. So these dimension 12 coefficients were coming to stuff which is order S to the 4th, which is the same order at which the logs appear. And the logs contain the square of this coefficient and this one. So it's better, you could leave those coefficients free, but it's more
constrained.
It's more constrained. It's closer to the actual effective utility you want to study if you fix the coefficients in the log to be exactly the ones that are required by elastic unitarity. This way, you're also inputting in some way when the inelasticities start, right? You're not allowing inelasticities too early. And so then if you want to impose them squared, then you need to fix them because that's not linear part of the answers.
Mm-hmm.
Okay, so this is why we have a plot as a function of F2. And F2 would go to -1 and 1. I'll show you a plot in a second, which is a bit more complete, but the region which converges well is a region which is close to 0. These ones are the error bars, which tend to grow to the sides. We can discuss this offline or later if you want to why they tend to grow in this direction and this direction. And here there's just some strongly coupled physics. So since our world has photons which are weakly coupled, not just at low energy, right? Photons are pretty weakly coupled because the alpha is small. And so even at the scale of the cutoff, they're still weakly coupled. QED is a weakly coupled theory after very large scales. So this is not our world. So this is some putative world where photons are coupled to matter, which is strongly coupled at low energies. So they're strongly coupled to matter at low energy. And there is a bound to how strongly coupled they can be. So this is essentially one of the non-trivial results of our numerical explorations. And okay, you could expand this in many directions. You could study what this theory looks like, for which the numerics here is pretty hard. So we don't have enough convergence to actually study the partial waves here and see features which are well converged. So it would be interesting to push that. It would maybe be interesting to do this in say lower number of dimensions, where you do expect some more strongly coupled situations, say in condensed matter theories, photons interact with material. But in any case, this is the statement that there are indeed the non-trivial constraints coming from completely non-perturbative unitarity on the low energy effective field theory of photons. Okay, I don't want to spend too much time on the extrapolation. I just want to tell you that it's hard. In particular, this is sort of a explanatory plot of what's happening, why it's hard. So you remember that there were two parameters that were fighting each other. One was Nmax. Growing Nmax, we go down here. So we're computing the minimum of G bar 4. This is exactly the plot I showed before. Say like a piece of what enters in that plot, like for each point of the plot before. And so the minimum is smaller and smaller, less and less constrained, the more we increase the ansatz. Of course, we're giving more freedom to the ansatz. And then instead it goes up when we increase the number of constraints, Lmax. So in principle, you would like, you could imagine that you can just push these ansatz, you can just extrapolate, fix Nmax and then extrapolate to zero. Just extrapolate to zero, and then increase Nmax and get a conversion scenario. And this is what people were seeing before. And probably people were seeing this before, probably because it was problems in which convergence was simpler, so they weren't seen far enough. But that's sort of like to be seen. So what I can say is that in this case, you do see a very nice plateau, and you might think, okay, this is a very nice plateau. I'm going to extrapolate here and then extrapolate down and get some value, some minimum. But in fact, this plateau is not a plateau, it's a runway, and then at some point you'll take off. So if you impose at finite Nmax too many spin constraints, then you lose completely the amplitude. It's not possible to just finite Nmax impose all the constraints in unitarity, which you might have foreseen or not. In any case, you need to find a way around this. And one way that you can imagine is to just extrapolate on the plateau, right? But the thing which is important here is that this plateau gets longer and longer the more you increase the ansatz. So maybe a better way to extrapolate is sort of sideways. It's something like this. You want to extrapolate this way. You want to increase the ansatz and the spin constraints at the same time, and then essentially see where you get. And this is what we did as a working hypothesis on how to make this extrapolation. Let's leave alone the plot above. It's just a version of this extrapolation, and we can see maybe a couple of more plots and then go to the last part. Well, actually, I think I have maybe less than 5 minutes, so I will just tell you very briefly about the last part. So this is some other plot in which instead we're looking at the minimum G bar 4 still, because we know there is a minimum, but now as a function of F bar 4. So you can also do that. And again, you have a strongly coupled region in which something non-trivial is happening. And then these dotted lines are weakly coupled prediction that I'll get to in a moment. So you have that asymptotically, you're getting closer to this weakly coupled prediction, and then there is some strongly coupled region at low value of G bar 4. So the physics is more or less uniform to the one before. This plot looks, it's very well converged. And okay, if you put together these plots, you'll get both or half of a boat. So this was like this f bar 2 and f bar 4 are the two parameters for which I showed plots. These were sort of slices of this guy, and then g bar 4 was the and there is a symmetry of f bar 2 into minus f bar 2. So this really looks like a boat. So allowed amplitudes are above this boat. And this is the space of effective field theory of photons. And if there is a boat, there better be a shore. So if you instead now put g bar 4 prime, you'll get a different plot. And there are also bounds there. Of these bounds, I only want to emphasize one feature, which is that they're very well converged when g bar 4 prime is positive. So if you look at the minimum again of g bar 4 as a function of this other coupling, the thing to bear in mind is that when the coupling is positive, we have well converged bounds. When the coupling is negative, the error grows. This is rubbish. We cannot trust it. So bear in mind this for a second, because it will come in handy in the last part, which is this part, which I'll go through quickly, and I'll just emphasize the important parts. So what is the name of the game now is to explain why we cannot rule out a lot of this space, why these bounds are so always one-sided, etc., at least as best as we can. And the way to do this is rule in part of the space, right? We want to find amplitudes that actually live around there. So although we don't know any strict recompletion of QED, QED, I shouldn't say QED, of say photon scatterings or Euler-Heisenberg. We can play the game I was saying before and add the resonances. Let's say some tree-level resonances or some charged particles that run into loops. And if we take this coupling to be small, we can really just focus on tree-level or one loop. So we can take spin 0, spin 2 resonances, and we can take scalar vector and spinor QED. And this is very close, essentially the same, with some twist that was done in these papers at some point when they wanted to compare to their bounds from analytic bootstrap. And okay, essentially the main feature to remember of these things is that all the Wilson coefficients are homogeneous in the coupling, because you have those amplitudes were proportional to a coupling squared. And so the low energy theory was coupling squared times s squared plus s cubed plus blah, blah, blah. Right? So all these low energy coefficients are proportional to the same power of the coupling. And this explains why all these couplings go to infinity so all these Wilson coefficients go to infinity as lambda goes to 0. So this means that the perturbative amplitudes mark unbounded directions in the space of effective field theory. And this is something that is obvious, but it doesn't tell you yet that it cannot be bounds, right? This we knew, but okay, you have some direction which is covered by effective field theory. Maybe some others are not. In particular, for instance, in the case of G4, we know there's a minimum, so directions with negative G4 are not covered by weakly coupled effective field theory. And so then the game is to look for these perturbative amplitudes, take all possible linear combinations of them, and look how much of this space you can fill. The results of this is that dimension 8 I already explained. At dimension 10, there is some combinations of the theories that I was telling you about that cover all the space at infinity. And then this means that there are no numerical bounds. Remember that this is even more. It tells you that there cannot be numerical bounds, neither upper nor lower bounds, right? Because I'm saying, let's say there's a sphere at infinity in this space. This sphere is all covered by theories. You could imagine, is there some disallowed region at the core, right? Some minimum value that I cannot find, but that's impossible by convexity, right? I can take a theory here and a theory here and draw a line. And the theory there will be a linear combination of those two. So once you cover the whole sphere, you just don't have any bounds. And then at dimension 12, you do have that only a portion of the space is covered. And in particular, this agrees, for instance, with this plot that I showed before. So if you take the minimum value of G bar 4 as a function of F bar 4, I was telling you there is the dotted line, which is a perturbative amplitude. This is the boundary of the space that we find with this ruling-in procedure. And at infinity, the direction is the same as the numerical bound. So really, this plot is telling you that this weakly coupled physics persists until very small value of G bar 4 and F bar 4, where perturbative means actually going to infinity. And then very close to zero, there is some non-perturbative effect, which is this curvature. The fact that while this weakly coupled theories meet at cones, here there's a rounded off region, which is nonlinear physics. Very last plot before the conclusion. You remember that we had this well, actually, I want to tell you two things. So we remember that there is this story of G bar 4 prime positive, where the amplitudes are well converged, and instead all the perturbative amplitudes we know of have G bar 4 prime negative. So there is no intersection between what we know and what we find numerically. So this is the place where it's really necessary to just keep going, trying to find new amplitudes in this region. But what is even more interesting about this is that if we compare with the analytic results, this is G bar 4, sorry, this is this dimension 12 coupling G bar 4. These are the perturbative theories that we have, and these are bounds from the papers that have done analytic bootstrap. And you see that the strictest bound just exclude completely all the region of G bar 4 prime positive. So in particular, they exclude completely, well, some of our amplitudes, we can discuss this maybe offline, but also all the perturbative amplitudes that are well converged numerically. So there is no strict contradiction here, because those papers have to assume essentially three-level physics. You cannot include consistently loops in those methods yet. And so these bounds are not in contradiction with the existence of theories which have one loop logs, as we put, and G bar 4 prime positive. But this does tell you that the modification of these bounds when you include loops, just even the low energy effective theory loops, essentially when you allow the coupling to go down, the mass gap to go down, well, the modification is not small, right? It's order 1. There are theories all the way here, if you don't make a weakly coupled assumption. And then, okay, the best possible word will be some interpolating physics, which tells you that when you push the strong coupling physics all the way to infinity, you get these bounds, G bar 4 prime negative. And when you start lowering it, there is some systematic analysis that will tell you that this region then will be included. But then there is a question, is this region only included a little bit of it if you lower a little bit the mass scale, or is just everything goes once you don't assume just three-level physics? So this is sort of something for the future, but it needs to be discussed. Okay, so let me conclude. What did we do? Well, we asked ourselves what are the possible effective field theories of light, and such that the UV completion exists. And the partial answer is that there is a lot. Like if you just look at 2-to-2 scattering, there are unbounded directions, and some of them are explained by perturbative amplitudes, although for the moment not all of them. There are one-sided bounds on some OP, not OP, Wilson, that's a different context. Some Wilson coefficients, for which there are no dispersion relations. This I did not emphasize, but not all of those bounds, well, the dimension 12 bounds you cannot get via dispersion relation unless you assume three-level physics. And in particular, there is some perturbative analysis which is not compatible with our constraints. So the loop effects on the null constraints can be big. This is something like essentially what we have showed. And so it would be nice to sort of systematize the perturbative analysis to include this one loop and higher loop effects and see if one can bring this again to agree. The numerics was pretty hard, so maybe there's room for using a different ansatz and a motivation to develop a dual method for this case. And then, okay, it would be nice to sort of, if from the analytic method one should get closer to allowing more strongly coupled physics, it's also true that we would like to maybe get closer to our world, so put a different set of assumptions. And there's recent work in which something like this was done by inputting a bound on the imaginary part of the amplitude. It would be nice to do this as well, maybe here, as sort of impose that the imaginary part is small, that there is weak coupling up to some specific scale, and then use that scale as a parameter. Or maybe one could even think of going a bit further in effective field theory and add E plus and E minus contribution explicitly in the ansatz, in the loops. And finally, all of this is a good warm-up for quantum gravity. So, okay, it's not an easy problem, but the technology is there. So thank you very much for your patience and letting me go a little bit over time.
Okay, let's all thank Marco. And now I think we have time for a few questions.
Do you think it's feasible to do spin 2 or just some problem that, okay, it exists? And
if it's possible to do spin 2, that's the question.
yeah, it's
like technically possible.
Yeah, technically speaking.
I think it should be. I mean, the point is convergence, because more amplitudes means more. Well, okay, let me first say the obvious thing. You cannot do spin 2 in 4D if you're not very smart. By very smart means nobody knows how to do it at the moment. And the reason is that the graviton is charged, spin 2 particle self-interacts, so you don't have infrared-free stuff, so you're going to have massless particles interacting in infrared, and in 4 dimensions, this has infrared divergences. So you cannot use single particle states as asymptotic states. You'll need to use some dressing, but then you need to understand analytic properties of this dressing and unitarity for it. So this is some work that is conceptual work. So maybe there is a different basis, maybe it's celestial CFTs, maybe it's Fadeev-Kulish style, but there is some place where there is the appropriate basis of asymptotic states to treat this problem, but it's not the standard partial waves. In higher D, you can do that. And in higher D, then the problem is just convergence. I think what our paper showed is that convergence tends to be very hard when you have a lot of amplitudes, and so a large number of coefficients in even at low spins. So in each partial wave, in each partial wave. So, okay, there is, I have to say, a little bit to think about here as well, because there's also, we didn't quite understand if it's just a generic feature of, say, large number of amplitudes, or if it's something specific, say, to the logs, to the fact that the ansatz, right, we put in logs that have a specific non-analytic behavior and a specific growth, and then we're trying to balance it off with our ansatz, with the Ross series. It's not obvious if there are problems in convergence that are introduced by the logs, although we tried to turn off the logs and it was not improving much. I mean, there's room for experimenting, and it would be nice to see other papers in the future where the numerics is maybe pushed further for the scalar amplitude and see if this takeoff happens. So, okay, so assuming that the convergence is just a general problem, then it's going to be also even more enhanced in the case of the spin 2. But honestly, I don't think that that is a stopper, because, for instance, here there was very clear plateaus. What is the convergence problem? The convergence problem is that at some point the plateau is over. Then we can take this working hypothesis that the right way to do it is to increase Nmax and Lmax at the same time, and we were able to extrapolate. Maybe in gravity the plateau will be shorter because you have even more coefficients, possible, but it probably is possible to just do something, let the computer run for a longer time. I don't see a very big problem. The big problem here is, again, you want to impose, if you want to get closer to our world, weakly coupled physics, still keeping the full nonlinear unitarity equations. So I think, yeah, one would need to get the right problem in order to corner our world, rather than, well, you can also do just a first run like this one, completely non-perturbative, but you will not get Einstein gravity at the corner of the space.
But if you turn off, you were saying, if you turn off the log effect, if you turn off one loop thing, you can find bounds, right? You don't have that takeoff problem, or do you? You still have it?
No, I think it's not. Yeah, I have to look back at the logs and ask my collaborators. I don't remember in our first runs, because we were very interested in the correct physics, but I think we did try, and it was still. But okay, yeah. So yeah, what I don't remember if we tried and we failed because we were not pushing the numerics enough at the time, or if we did see the run away again. Yeah, it's something I need to look back to. I'm sorry, I don't remember.
Because I would say, if you don't have logs, then you would go back to the other cases where positivities and null constraints are enough, and
yeah. But I mean, this is all a bit of a. Okay, the reason why I did not look into this in detail is that it's a bit of a academic discussion, because the logs are there. And it's, if you turn off the logs, you just don't describe the right physics. And now, if you want something more specific, if you're trying to bound coefficients which appear at lower order than the first logs, then you can turn them off. And if you have them off and on, you get the same bounds. But those were the bounds that were very well converged. If you want to bound coefficients where the loop effects are important, then you need the logs. Otherwise, it's not even well defined, right? It's the coefficient, the effective coefficients, if there is a log, are only well defined once you fix what's the argument of the log, right? Because otherwise you shift mu and you get a contribution there. So it just doesn't make any sense. It doesn't make any sense unless you're assuming 3-level physics.
Yeah, I agree.
But yeah, so to some extent, this is academic. You do need the logs, so you better find a way to deal with this runoff if it's due to the logs.
Do you think that higher loops can help? Like, I know that if you go for higher loops, then you need to take into account inelasticity. But is it possible that higher loops would help with this convergence problem? Let's say we know what to do in elasticity, then higher orders would help. Do you think so? The problem.
I would not expect so. I mean, so okay, so there are some pieces of law. Okay, so let's think. If you were to impose that there are no elasticities, then it might, because what's the problem with the log is that, okay, you put a log, but then that's sort of there would be a log square, right?
Yes.
And the log to the n, etc. in the elastic part. And okay, this is also a bit reductive. So what you know is that the imaginary part will have some higher powers of the 3-level coefficients, but they might come from polylogs, blah, blah, blah. But this is sort of a technical problem. But if you were to allow for that, then you would be able to unitarize the amplitude to some higher order. And maybe you're pushing a bit the problem. But then again, you're not going to describe the most general physics. If you start allowing for inelasticities, then first you need to tell me what the basis of function is. But then if the coefficients of these logs are unfixed, I don't see how they could interact with the coefficient of the lower logs and fix the problem, right? There's a piece of that coefficient that unitarizes, and then there's something else. So I think it's not, in the most general case, there's no reason to expect that the problem gets better if you just include logs at higher logs or polylogs with arbitrary coefficients. I think it's just, this is hard. And okay, you can push the numerics, or and another good thing to do is to find the dual problem, because then at least you don't have the extrapolation in Nmax. Like anything you find is a bound, maybe it's a weak bound, but it's a bound. And you also can check if you're actually covering all the space with the primal. So I think that's more promising.
Okay, good. Any other question? Okay, if not, let's thank Mark once again.
Thank you.
Okay, thank you, Mark.
Bye bye. Thank you. See you.
See ya.